Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on November 12, 2025, just yesterday. This paper trains a vision-language action policy entirely in imagination, using a pixel-based video world model, delivering plus 9.8 and plus 15.2 percentage point gains, on average, over strong baselines. And on a tight insertion task, it reaches 70% success versus 53% for the base policy and 60% for DPO. The paper is titled WMPO, World Model-Based Policy Optimization for Vision Language Action Models, and the implications for robot training efficiency are quite significant. Also, the authors shared the official GitHub. You'll find full training code for WMPO and world models, task-specific examples, installation and requirements, single-node and array multi-node launch scripts, data and checkpoint download utilities, pre-trained VLAs, world models and reward models, plus evaluation scripts and configs to reproduce results and scale experiments. Alright. Figure 1 contrasts 3 ways to train vision language action policies and why the new approach matters. The left panel shows imitation learning, which copies demonstrations but cannot learn from failures, so errors compound. The middle panel shows real-world reinforcement learning, which can self-correct but costs too many interactions. The right panel presents WMPO, which uses a learned video world model, a data-driven simulator, to enable on-policy learning without real robot rollouts. Alright, Figure 2 shows the full WMPO training loop and why the policy can learn safely from imagination. The process runs in 3 stages. The policy proposes actions, the video world model renders the next frames, and the reward model scores each imagined rollout. Group relative policy optimization then updates the policy using group-wise advantages, which stabilize learning by comparing peers in the same batch. This loop repeats inside pixel space, so the visuals match the policy's pre-trained features. The result is on-policy reinforcement learning without real robot interaction. So, Table 1 compares policy optimization across 4 manipulation tasks and shows consistent gains. With a rollout budget of 128, the method reaches a mean success of 47%, beating GRPO and DPO. The base policy averages 34%, which indicates substantial headroom. With a larger budget of 1280, performance climbs to 58%, showing strong scalability. Across tasks, the bold entries for coffee, stack 3, 3-piece assembly, and square favor the same method, so improvements hold broadly. So Table 1 showed steady gains. Figure 7 shows that the learned video world model mirrors real robot motion for a tight insertion task, which signals faithful pixel-level dynamics. The top row presents the real-world trajectory. The bottom row shows the imagined trajectory, meaning frames predicted by the world model. The 2 sequences align in pose and timing, so the policy can train in imagination without drift. The task uses a 5mm clearance, highlighting precise predictions. Okay, 2 takeaways stand out. Training in pixel space lets the policy do on-policy learning safely in imagination, and the approach delivers clear, scalable gains, including self-correction and higher real robot success. The broader implication is cheaper, faster robot improvement with room for lifelong learning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.